I'm Eric Walenza, founder of IoT One, and this is the Industrial IoT Spotlight. Every episode, I interview one expert about a project that is impacting businesses today. Visit us at iot1.com to learn more, or email me to start a discussion. Welcome back to the Industrial IoT Spotlight. I'm joined today by David King, CEO of Foghorn Systems, the edge analytics solution provider. David, would you prefer to speak to a more general use case, or is there a particular customer that you have in mind that you think would be a good for this discussion?
Yeah, I can talk about a specific use case, and the reason I can talk about it with some attribution is because it will be unveiled at GE Minds and Machines at the end of October this year. And so, before we had to talk about it on more of a disguised basis, but GE, which is an early investor, actually the co-lead of Foghorn Series A, that's been integrating our technology into Predix, is now talking about this as kind of a proof point. So I can talk about a specific use case that comes from GE's Brilliant Factories program. This is their group that focuses on manufacturing automation and manufacturing IIoT use cases. So working with them and one of their end customers, we were able to basically go and attack a very, very high value problem for a manufacturer of very advanced equipment for the energy industry, right? Basically building capacitors and transformers for major electric utilities, right? The technology that runs the power grid. So this particular plant manufactures both capacitors and transformers. The capacitors have three stages of processing. There's an initial stage where they have a set of 6 winding machines that take the kind of aluminum material, wind it into coils. And you take those coils and you put them in a pack, and they call them a pack press. And that's the first stage of building a capacitor. Second stage involves, heat treating those pack press coils, for up to 6 hours in a very, very high temperature, high pressure oven, treat oven they call it. And there's a couple of these are very expensive ovens. These are, $10, $15 million pieces of equipment managed by PLCs. The winding machines are also managed by PLCs of a certain type. And then the last stage is the oil fill process, where after the pack pressed coils have been baked to a certain level, the completely dry and now conditioned pack presses get put. The final stage where they inject a certain type and amount of industrial grade oil that goes into these before they seal it and test it. So the problem statement that was given to us, right, and given to our GE colleagues was to go find out, where are end product failures coming from? Because at the end of this process, it still turns out there's a significant number of failures, really on a daily basis, where you've gone through these stages and you have a tremendous amount of IoT data being produced by each of these stages with very advanced PLCs, tons of sensors, right? Hundreds of sensors across the process. Actually, across the whole process, several thousand sensors, and across all the different machines. And you're still getting failures at the end product stage, right? At the end of the day. So the problem statement was, where are the failures occurring? Are they occurring in the winding stage, the heat treat oven stage, right, or the oil fill stage? And what we were able to do is working with the end customer in conjunction with GE is to install our product, our software technology running on top of a handful of HPE and Dell gateways next to each of these processes. And we started the treat oven, where the customer was convinced that there would be, the most failures because, several hundred sensors on each of these ovens, a lot of different stages of heating, a lot of what I call, dirty data being produced, where you have, dropouts of data out of order, data out of range, right? And so the customer was convinced that might be the source of the problem. Turns out, after doing investigation, where there were anomalies that occurred right in the data that didn't necessarily correlate using our machine learning technology to necessarily the end product failure state, right? We then went to the oil fill stage, which is the last stage where perhaps the spec wasn't tight enough, perhaps the operators, which are the most junior operators, weren't properly utilizing the equipment to put the right amount, the right kind of oil in. Turns out virtually almost no failures in that stage of it, right? The PLCs were fine, the machines were operating properly, operators weren't making any mistakes. It's very automated part of the process. So it turns out the most advanced equipment and the most advanced operators, the first stage and the winding stage, is actually where most of the failures were actually occurring, but unknown, right, to the operator, unknown to the the process system, the control system, and the data being produced with a very, very advanced PLC, a very advanced HMI, we're not catching a systematic bias towards over tightening, right, in the winding stage, right? So spec probably was a little off. The PLC, which was a very advanced PLC with a beautiful HMI, human machine interface, wasn't allowing operators to see all the different instances throughout the day where they might be over tightening, right, or even be given alerts to tighten even more when they shouldn't be, right? So it turned out that by running our software and little gateways attached to each of these stages of the production process, we were able to correlate failure conditions that were occurring at that stage with end product failure and figured out that the vast majority of problems in the winding stage. So that was a very, very high value use case. In the end, the customer decided because they do have a big knock on site, they necessarily have to run 10 or 20 instances of Foghorn all over the plant. They could actually run one instance in a data center and stream, several thousand sensors of data back, right, and run multiple use cases across all the different stages, right, in a data center environment. So the beauty of our stack is that it can get very, very small and run in like a half or a quarter of a Raspberry Pi. But you can also use that same stack in a big data center box and take in a huge amount of data and run many, many different models, right, all at the same time. So that's a very particular use case of a client of GE's that we were able to do this with. This is a very early proof point for us in the manufacturing world. But there's so many different use cases in manufacturing, whether it's discrete manufacturing or process continuous flow manufacturing. And of course, we've now gotten exposure through Saudi Aramco, one of our investors, to many, many use cases in the oil and gas domain and across the whole energy space.
And so on this use case that you just walked through, can you explain a bit more on the correlation process? My assumption, and it turns out my assumption was a bit off, was that you were primarily working in cases where you were able to work with the customer, develop an algorithm to solve maybe a known problem where previously it had been addressed with a kind of a mix of expertise and maybe cloud analytics, and you were able to take those algorithms down to the edge. But in this case, it sounds like you don't know what the problem is up front, so you don't have kind of functioning algorithms to identify it in real time, and you're then collecting data from a very diverse environment and aligning that with failures that coming off the end. Can you provide a little bit more depth into how are you correlating that? How does the processing actually work in this use case?
Great point. It actually can work either way, right? So if the customer or the industrial solution partner, right, has a set of pre-built algorithms, right, they've developed, and just an example, if this had been, say, a turbine use case, right, working with GE, they have thousands of data scientists and tens of thousands of models and algorithms built, right, to look at turbines and jet engines and such, which they've been doing for decades, right. Here we're talking about machines that aren't kind of traditional GE machines, and so we work with them and work with the end customers, operations staff to figure out what the specific problem statement was, right, to get knowledge of how the machines operate. So we did, in this case, have to kind of build the analytics rules and the machine learning algorithms from scratch, right? We had to take our data science knowledge, combine it with the customers in conjunction with GE to figure out where the problems occurred. But very often we go into domains where you've got algorithms that might have been developed for maybe a related or a similar type of machine or process, and you try that algorithm, right? The beauty of doing this at the edge is without having to ship huge amounts of data and huge amount of cost and cybersecurity risk to go figure out if the models are working, right, and iterate and improve them, you can actually do this processing, right, on the streaming data at the edge. So deploy the model, iterate the model, improve the model, and then at various intervals, take that metadata insight and push it back, right, to the original source of that model to improve that model that can be federated out to other machines that may be very similar to it, right? So this is the idea of connecting the edge, analytics machine learning layer with the cloud data science, right, is this closed loop machine learning or closed loop AI concept, right, that I think is going to play out in almost every domain.
Yeah, no, fascinating, because it's a much more flexible solution for companies that, as you said, haven't done the work that GE has done up front. And I think that's most companies out there. What were the time to results here? What was the deployment to being able to present your identification of the product failure causes?
Yeah, so, it was a matter of about to say a month to month or two for each stage. We started with the customer's hypothesis that the tree oven was going to be the predominant source of failures, and tried it there first, then went to the oil fill, and then finally came back to the original stage, which in theory would have been the least likely because you had best equipment, best PLC, best HMI, most experienced operators. In theory, the tightest process. So all told, it was a matter of 4 to 6 months of kind of experimenting to find the source of failure. It really will depend. If you've got a particular type of equipment, let's give examples like an ESP or a compressor or valve, right? That is your big source of machine failure or process failure. Right? You can just hone in on that particular process and start to find results pretty quickly. But a lot of it depends on how often the failures occur, right? If these are failures that occur, like in this case, on pretty much a daily basis, you can pretty much train a model at the edge because you're seeing enough failures. With a beefy enough server like an HPE or Dell server, you can actually even train the model that you don't have to go build a model elsewhere, sandbox it, and then bring it down to the edge. In other cases, though, if you do have a lot of sensor data, right? If you've got like in turbines and some of these other machines, you may have thousands of sensors, right? And you need a lot of high frequency data before you see a failure. In those cases, that's where algorithms built elsewhere, right? Sandbox in the data center cloud can then be imported down to run at the edge to iterate before you send it back. So it really depends on the use case, right, where you do this. But in this particular use case, there's enough failure conditions occurring, on a daily basis that you can actually build all the models and iterate them at the edge. Other cases, you really need to sandbox it first in the cloud.
One of the challenges that comes up quite frequently in discussion of, computing on the edge, certainly computing also in the cloud, is actually getting the data from a diverse set of sensors and being able to combine that. We still have some significant issues with standards, kind of a proliferation of protocols. Is this a challenge for Foghorn? Are you able to work with, is this a matter of you integrating kind of one by one with all the common protocols out there, or requiring that the customer is able to put that data into a kind of a standardized model? Let's say, how does Foghorn address this challenge of multiple protocols that are not standardized in the market?
Right. The heterogeneity of the data sources is, in fact, I think, then in many cases, stumbling blocks for certain companies to deal with. So, Foghorn's approach to this, I think, is a very elegant one. What we've done essentially is we have put some kind of pre-built agents or brokers into our data ingestion layer right at the front end, where you're producing data in some very common standard formats like OPC UA or MQTT or Modbus TCP. We've already got kind of a built-in broker to take the data in. But I think the real elegance of our approach is that we have what we call the custom agent or the custom broker that's also part of this, where with a very, the use of the SDK that comes with our platform, you can publish data from any source. So any industrial protocol source, any unstructured data source like video, audio data, right? You're talking about, different frame formats and, different interfaces, but all of those, including, reference data from, say, a SQL or NoSQL database, GPS data, RFID data, any data, frankly, can be streamed into our system using this custom interface. And I think this is what makes our system, so much easier to deploy than most, is that you don't have to spend a lot of time, trying to figure out how to get the data in, right? If you can, get the protocol parameters of the data source that you're talking about, there's a very easy way to basically publish that into our stack, right? And as soon as we get that data, often from like binary sources, we can, normalize that into a consumable data format, instantaneously. That's kind of the real-time normalization function that's part of our system.
That's great. I think a lot of the cloud platforms that were built previously have struggled in this aspect. At least this is what we've heard talking with end users who are often struggling to actually get their data up into a usable form.
Yes, that's a great point. I'd say that a lot of our cloud partners, and data science partners who operate in the cloud, are realizing that part of our value, frankly, is just the ability to, ingest, normalize, and condition data, right? And the kind of, I call it the data cleanup function, which is, data ingestion cleanup function, which is, from their standpoint, a difficult problem. It's just natively part of our system.
What are we looking at in terms of cost? I mean, I'm sure that the answer is going to be somewhere along the lines of it depends, but is there kind of a range in terms of let's say, a spot solution, an integrated solution that, across a large facility? What are we generally looking at from a deployment?
So our business model is subscription, software, so like a SaaS model type, and it's not based on, amount of data or duration of data. So as opposed to folks that are coming at this from a cloud perspective that try to charge you either on the amount of data being, persisted or processed, or, the amount of storage, or bandwidth required, we don't price that way at all. It's just a price per, subscription node, right? So any edge device could be an IoT gateway, could be a control system platform, right? So for us, it's really about volume and volume of devices and the kind of the compute footprint that we're operating in is where we kind of vary our pricing a bit. So I hate to say it does depend. If you're running us, for example, in that manufacturing use case I just cited, one instance in a data center, we charge a lot more for running one instance across a whole factory than if you put us in, say, 10 or 20 or 30 gateways sprinkled around the factory. And that, of course, is a different order of magnitude than if you're putting us, for example, we're working with a building automation company that has, over 1 million elevators installed all over the world. If you're talking about 1 million units running in a small, sub-Raspberry Pi size controller box, we charge obviously a lot differently per instance for that. So, I hate to say it really is dependent on volume and the kind of compute footprint we're given. And it could be anywhere from, I just throw some numbers out there, right? It could be, $1 a month. It could be $10,000 a month. It just depends on the use case, the volume, and the amount of compute that we're doing.
All right. Well, I might have to sign up for that $1 a month just to see how the solution works. David,
if you've got 10 million units of a machine, we'll definitely talk.
Let me ask one wrap-up question here. You're working with a lot of companies in different spaces. A lot of the companies that you're working with, I'm sure, are doing this in a POC environment, or they're also experimenting as they deploy. What is one thing that you see companies not doing that you think that they should be doing in order to improve their chances of success in terms of adopting fog computing?
That's a tough question. It's a great question and a tough one. I'd say that depending on when these customers are kind of made the decision to go down the digital transformation or IoT path, you get a different answer. So customers early on who were trying to solve big business problems and taking kind of a very, what I call high-level consultative approach, many of them have committed, lots of dollars and resources to try to do, predictive maintenance or, smart grid optimization, or, you pick the use case. And so there were some success stories, but there were also a lot of, kind of white elephants that, dissuaded others from kind of taking the big ticket approach. So I think the one thing that I would encourage, I think I said earlier, is, as you get started down this IoT digital transformation journey, start out with high value, high volume problems, right? High value or high volume, preferably both. But if it's something where you have a machine or process that has, failures that produce, tremendous, risk or loss to the business, that's not a bad, that's a good place to attack if you've got the data, right? To be able to identify where the source of the failure is coming from. Or you've got a machine type, I mentioned valves, compressors, ESP, pumps that are, failing a lot because these big rotating equipment, have mechanical parts and they tend to break down a lot. So machine downtime and process interruption, right, is the other thing to look at. So I need to pick high volume or high value, but in either case, you have to, have enough data, right, that's either being produced in real time that we can look at, or that's already been produced historically, right, in large data sets that can be used to build a model. That's the one advice is if you just try to, solve a problem without knowing kind of where the failure conditions are occurring, you could spend a lot of time in cycles and not find anything.
Great. David, let's wrap it up there. Thanks so much for your time. Really interesting discussion for me. And also, I'm personally very much looking forward to seeing where Foghorn develops in the coming years.
Okay, very good. Eric, it's really a pleasure to talk with you.
Thanks for tuning in to another edition of the Industrial IoT Spotlight. Don't forget to follow us on Twitter at IoT1HQ and to check out our database of case studies on IoT1.com. We help to accelerate digital transformation by advising business leaders on how to integrate IoT technologies into their operations and products. We appreciate your thoughts, suggestions, and of course your reviews. And if you have an interesting project, we'd love to feature you on a future edition. You can write me at eric.walenza@iot1.com.